Question 1, 10 mils of 0.5 molar potassium sulfate and 10 mils of 0.5 molar silver nitrate solutions are mixed, and the mixture is allowed to attain equilibrium. Which ordering of the concentrations of the ions in solution is correct? I know in year 11 that when you did ions, it exists in ionic compounds. When questions refer to ions, though, they mean it like this: ions in solution. Yeah. If you have ions in a compound, but it's not in solution, aka you use bracket S for it instead of bracket AQ, we consider the entire molecule because it's stuck together. You don't consider the ions floating around. When the questions ask you for ions, they want to know what specific stuff with positive or negative charge is able to float around and not sit stuck in a solid with something else. Yeah. When they ask for ions on its own. Okay. Now, in this case, you're mixing potassium sulfate and silver nitrate. Couldn't we just take these concentrations and multiply it by however many potassiums there are in 0.5 molar potassium sulfate? Wouldn't the ions that you put in just stay ions the whole time? Is anything happening when you mix potassium sulfate and silver nitrate? In this, yeah, double displacement, I'm going to need something a bit more specific though. You have the benefit of this revision of it being labeled module 8. What reaction did you learn in module 8 if you were mixing ionic compounds together? Precipitation, yeah? So this is a precipitation reaction in which you mix ions together, and some of them are going to come out as a precipitate, which means even though you put, let's say, 10 moles in, maybe 2 moles of them got used for the precipitate, and then only 8 moles of ions left are still in solution. The 2 that come out as precipitate, it's now stuck with something else in solid form. That's not the ions they're asking you about. They want free-flowing ions. So when they ask you for ions, they're asking you for ions from the original solution that it's in. If it came out as a precipitate, that is the moles of ions that you need to actually subtract because it's no longer in solution. So what is the formula for potassium sulfate? K2SO4, and at the moment it's aqueous because they told you it's molar. You can only express molar concentration for things that are aqueous solution anyway. You don't express molar concentrations of solids usually. And then also from your solubility rules, potassium sulfate is soluble. So K2SO4 aqueous, and what's the formula for silver nitrate? AgNO3, also aqueous, because they told you it's a solution anyway. And precipitation is a type of double displacement reaction. I just wanted something a bit more specific to tell me what's happening in the reaction in terms of states. But double displacement is what's happening where you swap it. So you're mixing potassium sulfate with silver nitrate. Imagine swapping the names yourself. What's the products that you're going to form? If you're mixing potassium sulfate with silver nitrate and the names swap, because that's what double displacement is. Silver sulfate and potassium nitrate, yes. And what's the formula for silver sulfate? Ag2SO4, thank you, Hadia. Ag2SO4. And what's the formula for potassium nitrate? KNO3. Thanks, Hadia. Thanks, Sandra. And now this is a precipitation reaction. They wouldn't bother asking you about the ion concentration if it didn't change, which means if it is changing, there has to be stuff that's coming out of solution. So there has to be stuff that's getting precipitated, which means there has to be something that's insoluble. AKA, there has to be something that you put bracket S on. Based on your solubility rules, are you going to put brackets S around Ag2SO4 or KNO3? Bracket S. Ag2SO4 because it's insoluble. It shows up on your KSP datasheet. All nitrates are soluble. All group 1 ions are soluble. So this one is aqueous and this one is solid. And whenever I'm doing stoichiometry work with chemical equations, before I proceed, I need to make sure that it's balanced. Thanks, Hadia. How do I balance this equation? A 2 in front of the AgNO3 and a 2 on the KNO3. Yes. Okay, let's keep on going. All right. Now, for the potassium and for the nitrate, they stayed as ions. So potassium is here, aqueous. Nitrate is here, aqueous. And then on the right-hand side, potassium, nitrate, aqueous. So it never exited the solution. It always stayed as ions. They didn't participate in the actual precipitation reaction. All it did was watch. What do you call the potassium and nitrate ions? Spectator ions. Very good. All they were doing were watching it. Thanks, Hadia, James, Sandra. Now, because all they're doing is watching it, they're staying in solution the entire time. They start out as aqueous and they end as aqueous. So I don't actually, nothing happened to its moles and nothing happened to its concentration. So it'll just be the same each time. So let's make a note here. Concentration of spectator ions don't change. Because the states stayed aqueous. Aqueous. Okay. Which means for K plus and NO3 minus, I can just figure out what its concentration is at the start, and that'll just be the concentration it is at the end. So I don't get given the concentration of potassium, though. I get given the concentration of potassium sulfate. How many potassiums in potassium sulfate? 2. So if I had like one bag with 10 marbles in it, and then I had 2 bags, that would be 20 marbles. So I times the number of marbles by the total number of bags. So likewise, if I know the concentration of the whole thing and I know how much of one thing is in it, I just times it. So the whole thing is 0.5 molar and there's 2 potassiums in the whole thing. So the potassiums is going to be 2 times the 0.5 molar. Don't use your calculator. This gives me 1. Yeah, thank you. And then I do the same thing with the nitrate. So the nitrate concentration was 0.5. And then what's the nitrate? You're not looking at the subscript 3 because the 3 only belongs on the oxygen. I want the entire NO3. So if you imagine yourself putting brackets around this, what would be the invisible subscript around the entire NO3? 1, yeah? So there's 1 nitrate in every silver nitrate, which means it's a 1-to-1 ratio. So the concentration of nitrate is same, just the 0.5 molar. Okay. So potassium is bigger, 1 versus 0.5. It's not equal to each other. So from there, I can immediately cross out A and B, and it has to be C or D. So it's either C or D. And unfortunately, I haven't cancelled out 3. I only cancelled out 2. Cancelling out 3 would have been nice, guys, because now that I have to figure out the concentration of my Ag and my SO4 that actually reacts, and I get given the information to calculate the moles of both reagents, it's not going to be a simple calculation. What do I have to check for? If I get given moles of both reactants, I have to do a limiting reagent and excess reagent check. Okay, so ideally we cross to 3 and just get left 1, but in this case we can't. So let's continue. So for potassium and nitrate, the concentration doesn't change. That's great. For Ag plus and SO4 minus, the concentration in solution, well, I should say the concentration remaining in solution to make it clearer to you. The concentration remaining in solution is going to be the concentration added minus the concentration reacted. You can do it in terms of moles first. Moles remaining in solution is moles added minus moles reacted. And the reason we'll do it in moles first, and then we'll convert to concentration after, is because your equation is read in terms of moles. So I want to do it in terms of moles, and I'll divide it by volume after to get concentration. So moles of Ag plus added is a 1-to-1 ratio with AgNO3, just like the NO3 was, is equal to the moles of AgNO3 added, which is equal to C times V, 50.5 molar and 10 mils. So 0.50 molar times 0.01 liters gives me 0.005 moles added. Because I'm calculating multiple things for the same chemical, I want to label my working out really carefully. I know a lot of you guys are mentioning silly mistakes resulting after when we got feedback from your trials. Don't repeat them. Yeah. Like if you're able to identify that to me, then don't let that continue. And one of the things we keep seeing is the not labeling your working out kind of stuff. Yeah. If you're able to identify it, that's the first step, but don't let yourself repeat that. So that's added. And then moles of AgNO3 reacted depends on what the limiting reagent is, which means I got the moles added now, but I need to know the moles of the other thing that got added, because the amount reacted depends on what the limiting reagent is. So I'm going to move this down because reacted depends on limiting reagent. Moles of K2SO4 added, C times V, same thing, 0.5 molar times 0.01 liters, 0.005 moles added as well. Does that mean there's no limiting reagent if there's equal numbers? Is this how I check for the limiting reagent? Yeah, you need to divide it by the coefficients first. Good. So if you divide it by the coefficients and they are the same number, then there is no limiting reagent, but you're not comparing the amount that you actually added. You're comparing the moles with the coefficient divided. So step 1 to identify a limiting reagent, calculate moles added. Step 2, divide by the coefficient. So AgNO3, you're going to take the 0.005, you're going to divide it by 2. That's going to be 0.0025. And then for K2SO4, you're going to take the 0.005 as well, but what's the coefficient for K2SO4? 1. Good. So I'm going to divide this one by 1. Okay, now, based on these two numbers, what's your limiting reagent? You're not comparing the actual moles added. I'm skipping a question. The limiting reagent is AgNO3. When you're looking for the limiting reagent, you're looking for the smaller number. So 0.0025 is smaller than 0.005 is less than 0.005. So therefore AgNO3 is the limiting reagent. Now, guys, this is a lot of work for a multiple choice question. Would you agree? Yeah, there's a lot of work for a multiple choice question, right? But like, here's the thing: is there? I'm gonna pause for a second. Is anyone able to think of a way of making this faster now that we've identified the limiting reagent? And I'll give you a hint. The question didn't actually ask you for the moles of everything. They didn't want specific numbers. They just wanted you to order it. I'm gonna pause for a sec. I don't want to have to do all of the working out. Reflect on what it means to be a limiting reagent. They don't want the actual concentration. They want the ordering of the concentration. I don't have to give them any numbers. This isn't a short answer question. What does it mean to be the limiting reagent? Good. The limiting reagent is the one that's all gone. So we've already crossed out A and B. Out of C and D, what's the answer? I can get to the answer without calculating concentration. D. Good. Okay. So one more time, guys. Number one, the question didn't ask you for the actual concentrations. Notice how all four options, there are no numbers. They just want you to order it. So as long as you have a general idea of what's in the beaker after the reaction's done, you might be able to figure out the ordering. We couldn't figure it out from the very start because we knew a reaction happened, so we needed to do a little bit of working out. Once we've identified what the limiting reagent is, by definition, from year 11, the limiting reagent is the thing that gets fully consumed. That gets fully consumed, which means none of it is left in the same state. Nitrate, we know, stays the aqueous because it actually doesn't participate in the reaction. It just stays aqueous the whole time. But this silver, we identified that silver nitrate is a limiting reagent. The silver component that actually gets precipitated, if it's the limiting reagent, if all of the silver that you added turns into solid form. That's by definition what limiting reagent means, which means if silver is a limiting reagent, it fully goes away. You can't have a concentration below zero. Nothing can be smaller than a zero concentration. So if you know that Ag is all gone, then it will have the lowest concentration and you immediately have to pick this answer and you don't even have to calculate the sulfate concentration. Can I get a thumbs up, guys? Does that make sense? We can go ahead and do the calculation if you want to prove the flow chart. But point is, I've figured out that Ag plus completely goes away. So it just has to have my smallest concentration. Can I get a thumbs up, guys? Does that make sense? This is a multiple choice question. I don't actually have to calculate everything. Yeah. As long as I know that it's gone, by definition, it just has to be the smallest amount. Yeah. You can't get below a zero concentration. So if I know it's all gone, I just have to pick the option where it's the smallest. And then for the potassium and the nitrate, you might be like, oh yeah, but we still have to do that. Yeah, we did still have to do that. Yeah. But at least for these two, you didn't have to do too much stoichiometry work for it. Okay. So watch out for if questions are asking you for the specific numbers, or if it's an ordering kind of question, you might be able to get away without doing every single calculation. If you want to challenge yourself, by the way, doing the entire calculation might be good. Now, one thing to note here, if this was a short answer question and it wasn't a 1 mark question or a 2 mark question asking you to give me the order. If it was just state the order, you can get away with just writing out what D looks like. If the question said prove or justify your answer with calculations, you would have actually had to go and calculate everything. Yeah. If you were to work out a multiple choice, how much time would you leave for it? Let's say like 5 minutes. If it's a calculation multiple choice question, you wouldn't expect to see too many of it. We're preparing for the HSC. That's why we're putting this stuff in. But you only get like 1 or 2 questions like this out of the entire 20. So let's say 5 minute max if you're actually working on it. If you're staring at it for 1 minute and you're not working on it, just go. Just go, okay? And then come back to it later. Yeah. We were progressing fine though. That's why we kept on going. But you don't want to keep on going if there's another way. Question 2, a solution that may contain, how vague, either 0.1 molar Ag plus, 0.1 molar Pb2 plus, or both, is treated with 1 molar aqueous HCl. A white precipitate forms which does not appear to dissolve in hot water. What conclusion about the cations may be drawn? Okay, a precipitate forms. Now, plus combines with plus charges or plus combines with minus charges? Plus combines with minus charges, good. Plus combines with minus charges. So then they're asking you about Ag plus and Pb2 plus. Are we concerned with it precipitating with the H plus or the Cl minus? Cl minus. Okay, so let's keep on going from there. Does Ag plus precipitate with Cl minus? Yes, so it's possible that Ag plus is there. Does Pb2 plus precipitate with Cl minus? Yes. So NAGSAG group 17, the second G in NAGSAG is group 17 or group 7, which is always soluble, but PMS is one of your exceptions. P is Pb2 plus, lead. S is silver, Ag plus. So Pb and Ag are exceptions. It does form precipitates with Cl. So it's possible that both of them are there, which means you cross out this one. It's not possible that only one of them is there because both of them are former precipitate. Yeah. But then it doesn't say that there's no option that says both of them are present. Only one of them is present. So I've already used my first sentence. Get that one out of the way. Then there's a second sentence. A white precipitate forms, we used that already. Let's ignore that. Which does not appear to dissolve in hot water. I'm going to ask a really vague question first to see who has an idea. What are they trying to tell you there? It doesn't dissolve, and I'll add a little bit of a hint in the way I ask this. It doesn't dissolve even in hot water. Yeah, it's highly insoluble, okay? So guys, from year 11, one of the things we said was if things react at like room temperature or even in cold water has very low energy, a very low temperature, which means if something reacts even in cold water, it's desperate, man. It really likes to react, okay? Well, then if things that are like playing a little bit more hard to get and you put a little bit more energy to it, over time, if you increase the temperature, it does start to react a little bit more. So if something reacts, even when you don't put that much energy into it, it means it really likes to react on its own already, and it doesn't really care what you do. It's just going to go do it. Normally, if you increase the temperature, it starts reacting a little bit more. But then if you get a situation where you increase the temperature a lot and it's still not enough to get it to react, it's incredibly unreactive. So this doesn't dissolve even when it's in hot water, which means it really doesn't want to, okay? It's really insoluble. So whether or not it's AgCl present or PbCl2 present depends on which one is more insoluble than the other. How might we confirm that? Because we've gotten to the end of the information. The next sentence is just a question. How am I supposed to figure out if Ag is more insoluble, Pb is more insoluble. Good, KSP. What KSP am I looking for? The one that's the answer, the one that doesn't dissolve in hot water. Do I want a bigger KSP? Do I want a smaller KSP? I want a smaller KSP. Good. The bigger the KSP, the more soluble it is. They told you here it doesn't like to dissolve, which means it's more insoluble. So I want a smaller KSP. Okay. All right. Tell me, you have PbCl2 and you have AgCl. Which one is the answer? Which one's more insoluble? Can we, do we know what AgCl and PbCl2 are? Pb is lead and Cl is chlorine. Silver chloride is more insoluble. Thanks, James. So lead chloride is up here, 1.7 times 10 to the minus 5, whereas silver chloride is here, 1.77 times 10 to the minus 10. It's a way smaller KSP. Minus 10 to the minus 10 is way smaller than 10 to the minus 5. So silver chloride is way more insoluble than PbCl2. It's way more likely to not dissolve in hot water. So it's more likely that Ag plus is present and Pb2 plus just might be a little bit present. Okay. Question 3. The amount of chloride ion in a water sample is to be determined by adding excess silver nitrate. Do I have to do a limiting reagent check for this question? No, because they've already told me that it's excess. So if the silver nitrate is in excess, there has to be one limiting, there has to be one excess. So if they've already told you what's excess, the other thing's just going to be limiting. So it's always nice when you see this. So celebrate this if you see it in your exam. If 1 gram of silver chloride is precipitated, what mass of chloride ion is in the original sample? What syllabus dot point is this on? Starting with a G and an A. 2 words. Gravimetric analysis, yes. So you have chloride ions mixing with silver nitrate. Silver nitrate, James gave us the formula for it before. And then you swap the ions again. AgCl gets precipitated out. And then you have NO3 minus coming out. Okay. We can treat this like a stoichiometry question. They've given you information for silver chloride. They're asking you for chloride ions. I need a chemical equation, number 1. And number 2, I read my chemical equation in terms of moles. Yes. So I can't be like, oh, 1 gram of silver chloride, it's a 1-to-1 ratio. It's going to be 1 gram of chloride ions. It's a 1-to-1 ratio of moles. Thanks, Curdy. So I'm going to go into moles. Moles of AgCl is mass on molar mass because they've given me 1 gram. 1.0 grams over silver, correct me if I'm wrong, 107.9 plus 35.45 grams per mole. What do we get for the moles of silver chloride, please? Point 0.006975 mole. And then it's a 1-to-1 ratio. 1 here, 1 here. So the moles of Cl minus is the same. Moles of AgCl is 0.006975 mole. And then now that I've got to the correct chemical, I can convert back to whatever it is they want. I've gotten to the chloride ions, they want mass. So mass of Cl minus, I'm going to rearrange this, is moles times molar mass, the 0.006975 times just the chloride now, because that's the chemical I'm after, so just the 35.45 grams per mole this time. What do I get for mass of chloride, please? 0.25, thanks, James. And my answer is A. All right, any questions, let me know. Question 4, an aqueous solution of copper sulfate is a clear blue color. They don't really have to tell you that. You know the flame color, the solution color is the same, so it could have been omitted. The concentration of this solution is to be measured using UV visible spectroscopy. An aqueous copper sulfate solution will, if it is a blue color, when we did this in module 8, if it's a blue color, is it letting blue light pass through or the opposite color light pass through? Pass through. Pass through means that it goes through the solution and comes out the other side and goes to your eye. So let's put it this way. If it passes through, it can travel to your eye. So think of it as almost like a ball. If the ball was able to pass through, it would hit you on the other side. So if it passes through, you can see it. And then if it gets absorbed into the wall, it doesn't go to you. Can't travel to your eye. So that's right, Curdy. If it's a clear blue color, then it's allowing that blue color to pass through the solution, and it will absorb every other color of light, but it absorbs mostly the opposite color that it is on the color wheel. The opposite color, I don't really want to say opposite, it doesn't sound that great. Instead, I would say the color opposite it on the color wheel is called the, who's done color theory or paid attention in art class from year 9 and 10, the complementary color. Good. So it'll allow the same color light to pass through, and it'll absorb mostly the complementary color. The complementary color of blue is usually red. If you remember the color wheel though, does anyone remember what the actual opposite color of blue was on the color wheel? It wasn't actually red on the dot. Who remembers? Because we did this. Yeah, it was actually kind of orangey. Okay, so we normally think of red and blue together, but that color wheel that we had in the notes, orange was actually more directly opposite blue, and then red was like a little bit to the side. Question 5. The UV visible spectrum of a solution of a certain compound is shown. Consider the following statements about this compound and its UV visible spectrum. Which of the above statements is true? The amount of light absorbed by a solution of this compound depends on its concentration. True or false? True. What's the law that relates absorbance of light to concentration? How do we know it's true? Beer-Lambert's law, exactly. This is a Beer-Lambert's law question. Absorbance is epsilon length concentration. Concentration is a function, absorbance is a function of the concentration. If you increase concentration, you increase absorbance. So 1 is true. So it's you cross out B because it's either only 1 is mentioned in A, C, and D. Number 2, the amount of light absorbed by a solution of this compound depends on the wavelength of light used. True or false? True. Good. The graph that they've given you is a function, not a function in this case, not an equation, is plotting absorbance versus wavelength. So if you pick this wavelength, the absorbance is higher. If you pick this wavelength, the absorbance is lower. So the wavelength you pick does affect the absorbance of light. So number 2 is also true. Now, even if you weren't given the graph, we know this because That's the reason why when you're doing colorimetry, you always pick the opposite color, because we said if it's blue, yes, it will absorb every other color, but it'll absorb mainly the red color. It'll absorb the opposite color the most. Same thing applies for the other types of energies. So can't cross any out because A, C, and D both mention statement 2. Number 3, the spectrum is a result of electrons falling back from higher to lower electronic energy levels. I'm going to give you a second to think about your year 11 theory and what it means to absorb. Is 3 true or false? True? Why is it false? Hadia, plead your case.
I just remember when there's more energy, they go up.
Yeah. But then how does that relate? James, is it false when it falls back to lower, it emits light? Yes, which means that's a transmittance of light, but the graph is plotting absorbance. Good. So absorbance by definition means you're going low to high. Electrons normally start low and they go to high. When they jump from high back down to low, that's transmittance. So absorbance is when you're, by definition, absorbing energy. Absorbance, yeah, put it simply, absorbance is absorbing energy. If you're absorbing energy, you start low and you go high. But this question mentions start high, go low. This would be transmittance. What's the only graph in module 8 that plots transmittance instead of absorbance? So this one's not true. Have a think. I'm talking about spectrums. Oh, not that kind of spectrum. I'm talking about like the spectroscopy ones, not the qualitative tests. I'm looking for a quantitative technique that plots transmittance instead of absorbance. I'll give you the list. Colorimetry, UV vis, atomic absorption spectroscopy, mass spec, infrared, NMR. Which one was it? Where the graph looked upside down because it was plotting the opposite thing to the other ones. Yes, infrared. Infrared is the only one that plots in transmittance. Most of the graphs plot absorbance. So you cross out C because 3 is not true, and IV, the concentration of a solution of this compound can only be determined by UV visible spectroscopy at 250 nanometers. True or false? What's the word you want to be careful of in statement 4? Only. False. Good. Okay. Is 250 nanometers the ideal wavelength to set? Yes, but it's not the only wavelength you can set. You can set any wavelength as long as it absorbs some and it's not like touching here where it's 0. It's not the only wavelength. It is the best one though, but the word only is the issue here. So 4 is not true and your answer is A. So one of your key learnings from this question, besides all of this stuff, is watch out for any questions that use very definitive wording like this. The chances that there's only one way of doing something is very, very slim. All right. Question 6. The graph shows the absorption spectra of 3 food dyes: blue number 1, red number 2, and yellow number 4. Which one of the following is the best wavelength to determine the concentration of red number 2 dye in a solution containing a mixture of all 3? Now, if red number 2 dye was on its own, without the yellow number 4 and the blue number 1, what wavelength would you use? If red number 2 was on its own, what did we say? We always want to pick the wavelength with what kind of absorbance, starting with the letter M. Maximum, good. We always want to pick the wavelength of the maximum absorbance because it gives you the best reading. So red number 2 would be what? About 540, yeah, hits about 540 on the dot straight away. The only issue is, though, at 540, what else absorbs? Because we were just imagining it being on its own. At 540, it's not on its own, though. What else? Yeah, it hits the graph for the blue number 1. So if red was on its own, I would pick the maximum wavelength. You pick the maximum wavelength that doesn't interfere with anything else if it is existing with other things. So because it's existing with other things, you want to pick the highest wavelength that the others don't absorb, which means, unfortunately, yellow is here. I have to cross out anything here because yellow absorbs there. And then blue is blue here. The blue one is here, so I have to cross out everything here, which means this is the only section left that's just red. So guys, your answer is about 500-ish. That's really your only window. Yeah. So your answer is B. So guys, in summary, highest wavelength of highest absorbance as long as something else doesn't absorb it, which means if you get a question where it's in a mixture, just cross out the sections that others absorb immediately. You don't even want to look at that. And then the only thing I'll note for you is read the question carefully. When I tell you certain things about certain questions, it's specific to that question. If another question is not identical, you can't always apply it. Yeah, just like when we were doing module 7 in the first hour, we were doing that acid plus amine question, and then we went on to that next flowchart question. It wasn't a neutralization reaction. So my warning is, if you go into the exam and you see a graph like this where there's multiple spectra, please read the wording carefully. They might be giving you a graph with 3 lines on it, but the situation in the wording of the question is it's on its own, in which case you can ignore the other graphs. Can I get a thumbs up, guys? That makes sense. Just like I told you at the very start, when we were just looking at the red and you ignored the yellow and blue. Yeah. I don't want you to don't make assumptions about what the question's asking you, is basically what I'm saying. If you see 3, confirm in the wording of the question that the context itself is about 3. If not, they've just put it in there to confuse you. You're only dealing with the one graph, yeah? Be careful with that. Question 7, precipitation titrations are based on weighing the mass of the precipitate obtained during precipitation. True or false? Or does that sound correct? When we've done precipitation titration questions, have you had the mass of the precipitate in the question? Yeah, mass of the precipitate is a little bit more of a gravimetric analysis question. Now, the reason we might be getting confused about this is because with precipitates, we normally do deal with mass. It's just that with titrations, though, we don't actually care about how much is in the conical flask after it's done, guys. What do we actually care about? What's Yeah, the burette and the volume that comes out of the burette. So we're normally concerned with how much stuff you're adding over time. And then as long as you know the concentration and the mass, you can figure out, as long as you know the concentration and the volume from the burette, you can figure out the mass of the precipitate. But it's not really the main goal. It just so happens that it's a precipitation reaction. You don't really care about the mass though. So not really. Is based on reactions that produce complex ions. Do we make complex ions when we're doing precipitation titrations? No, precipitation reactions and titrations make precipitates. That's a complexation reaction. Exactly, Cody. Good. That's a different part of the syllabus. You've been able to identify that it's a separate syllabus dot point. That's a really good way of getting to the answer as well. That's not even correct. C is based on reactions that produce ionic compounds of limited solubility. True or false? If you can't figure it out, by the way, you can swap it and see if the other one is true. Yeah. So you're not able to tell me if C is true or false. So I'll ask you the opposite. Is it based on reactions that are very soluble? Or is it based on reactions with ionic compounds that are very soluble? No, because you're trying to form a precipitate in which it's limited solubility. Yeah, so if you say no to very soluble, then vice versa must be true also. It must be yes to limited solubility. Now, the reason you might be getting confused with this is because with part A, we agreed that you don't actually care about the mass of the precipitate. A and C are worded differently though. Worded multiple choice questions tend to be a lot harder because you're like arguing about, it's like comprehension in a chemistry test. But anyway, A is saying you want to figure out how many grams the precipitate is. That's what A is saying because you're weighing the mass of it. C doesn't say that. C just says the reaction that you're doing, it makes stuff that doesn't dissolve very much, which is true. That's what a precipitation reaction is. Yeah. That's what we said in A as well. We said, I don't care what mass gets made. I just care that a mass gets made. That's what C is saying. C is saying, I'm doing a reaction that doesn't dissolve very much. So a mass does form. C doesn't say, I care how much mass got formed. That's what A said. That's why A was incorrect. But C just says, you're making a mass, which is what the whole point of precipitation is. Can I get a thumbs up, guys? Does that make sense? It's based on the wording of the question. Yeah. A cares about how much you're making. C doesn't care. C just says, I'm making something that does precipitate, which is the whole point of a precipitation titration. So your answer is C. And then D is based on reactions that produce ionic compounds with a large KSP. True or false? Based on your answer to C. False, okay, because we said, yeah, exactly, Cody. False, because large KSP means it's very soluble, and we already agreed that we want something with limited solubility. Okay, so C and D was easy to figure out. So be careful of the wording of the question. And then question 8, which of the following statements about propanal and propanone is not correct? A, the compounds produce different patterns in the fingerprint region of the infrared spectrum. True or false? False. I put an asterisk on that. B, the compounds produce different fragmentation patterns. Yeah, they do have different functional groups, but where do we normally look for the functional group? Guys, I like the questioning. Where do we normally look for the functional groups though? Because they didn't say outside. What did they say, guys? What region of the infrared spectrum did they say? Ah, in the fingerprint region, yeah. Now, that functional group that you're talking about, does it show up in the fingerprint region? No, okay, because when we look at functional groups, when we did infrared, we always said ignore the fingerprint region. So you're right, they do form the same functional group. So to the left of the fingerprint region, they would show the same thing. But in the fingerprint region, which is what the question is asking about, they would show different things. Fingerprint region is all the little nitty-gritty stuff, like your fingerprint, that's always different for everyone. So they would produce different ones. That's actually correct. The question's asking you for incorrect. B, the compounds produce different fragmentation patterns in a mass spectrum. True or false? True, because they're just physically different. If they're physically different, they just break apart in different ways. C, the compounds have molecular ion peaks at different mass to charge ratios on an infrared spectrum. I'm going to assume that's a typo. Otherwise, C is just immediately wrong, yeah? Because molecular ion peaks show up on a mass spectrum. If it was genuinely infrared spectrum, that sentence would just not be wrong. But let's say mass spectrum. The compounds have molecular ion peaks at different mass to charge ratios on a mass spectrum. True or false? False. Why? Propanol and propanone, propanol and propanone, even though they have functional groups in different spots, they are functional group, last word starting with an I, isomers. They have functional groups in different spots, but if you were to draw it out, you'll notice that the only thing that changes is that spot and everything else is the same. If you try to fill out the hydrogens, you'll get the same number of hydrogens. They're isomers, they have the same mass. If they have the same mass, they end up with the same molecular ion peak. B and C are different because the question said fragmentation patterns, which is every single peak. Molecular ion peak just depends on molar mass. So they do have the same one. This question says they have it at different ones, which is not correct. The question's asking you for not correct. So C is your answer. And then last one, D, the compounds are functional group isomers and would produce different signals for the CO bond on an infrared spectrum. True or false? True. False. They are functional group isomers. So this part is true. And here's my question then. We've talked about this before. NESA has released, I don't remember which HSC it was in. It might have been in my HSC. One of the past HSC papers, they considered aldehydes and ketones as functional group isomers. So I know we call it the same name, like carbonyl, but they consider the aldehyde and the ketone functional group as two different ones, even though it looks the same. So they are functional group isomers. But then the second part, produce different signals for the CO bond. Does your HSC data sheet distinguish between a CO for an aldehyde and a CO for a ketone? No, it actually doesn't. So if you go to your data sheet, it just says CO. Now it does distinguish OH for alcohol and acid, but it doesn't do that for COO. It just says as long as there's a COO bond, it's going to show up here. So even though they're functional group isomers, the infrared spectrum doesn't distinguish between an aldehyde functional group and a ketone functional group. It just sees the bond as the same thing. So it would actually just produce the same signal. Okay. All right. Can I get a thumbs up, guys? Does this question make sense? 9. The most appropriate technique to determine levels of the Pb2 plus ion in blood is. So this is a different kind of spectroscopy question, one that we haven't dealt with so much, partly because this relies on you having done all of the techniques already and knowing what the different types are. So, you thought that you finished everything and then there's always something new. Okay.
Yeah.
Have you noticed that in the classes? Are we doing revision and you're like, where are
Yeah.
all these questions coming from?
Yeah.
Yeah. Well, there you go. This is the yeah, I realized that. I was like, so this is revision, but it's not really revision. Yeah. Well,
Exactly.
a little bit of both. So
Mm,
this is similar to module one separation techniques,
uh,
where you need to know what it is you're separating in module eight, what it is you're identifying, and what technique allows you to do that based on what the different techniques do.
okay.
But for you to know the correct technique, you need to know what the properties of the mixture in module one and of the solution in module eight is.
Okay, yeah.
Now, they're asking you for levels of Pb2 plus ions in blood. Let's go through it one at a time. Mass spectroscopy. What information does mass spec give you?
Like molar mass?
Molar mass. So if something has different molar masses, then if you use molar mass, you'll figure out if it matches this one or if it matches that one, which means you normally use mass spec to identify what something is, not determine the concentration.
Okay, yeah.
Yeah. And then also we aren't identifying two things anyway. They know what it is. It's Pb2 plus.
Yeah.
So don't need that. B, what does infrared spectroscopy gives you?
Like the functional group?
Functional groups, which means functional groups is something we apply to what branch of chemistry? Organic chemistry or inorganic?
Organic?
Organic, but lead is
Inorganic?
inorganic, so infrared doesn't work. Atomic absorption spectroscopy.
That one measures like the concentration,
Yes, go on.
like of a specific thing, like in the mixture.
Yes, for atomic absorption spectroscopy, you need to know what something is. You need to select the correct hollow cathode lamp. For atomic absorption spectroscopy, if you're testing for lead, you need a hollow cathode lamp made out of lead.
Okay, yeah.
Good. So at the moment, kind of seems like it's atomic absorption spectroscopy. It also works for inorganic substances, which is what Pb2 plus is. D, high performance liquid chromatography. We don't study this. We've already figured out the answer. It's C. If this was a HSC question, we would have had to just change that to another technique. It might just replace it with colorimetry, might just replace it with UV vis, might just replace it with like NMR or something.
Okay, yeah.
But just out of curiosity's sake, you've heard of chromatography before?
Yeah.
Heard of it? Yeah. Do you what have you heard of it from? Because there's one like really easy common experiment that people do for chromatography. Have you
Uh,
ever seen that? Like you put a marker on like a piece of paper and it
yeah.
spreads out into the different colors.
Yeah.
Yeah, so chromatography is used for separation of things that move at different speeds. The reason it separates is because like maybe red moves slower, so then it gets stuck behind and then the blue kind of shoots ahead on
Okay.
along the paper, which only works if there are different components in a sample as well. If you already know and it only contains lead, you don't really need chromatography for that.
Yeah.
So your answer for this one is C. Any
Yeah.
questions?
No.
And then 10, another one. Petrol is a mixture of hydrocarbon molecules varying in size from 6 to 10 carbon atoms. Forensic investigators suspect that traces of a substance found at a suspicious fire could be petrol that was used to start the fire. Which one of the following techniques could best be used to identify the substance? A. NMR spectroscopy. What does NMR spectroscopy give us?
That's like it's like the different chemical environments and
Of what atoms or what elements?
of carbon and hydrogen.
Carbon and hydrogen. So that matches. There are carbon atoms here, there are hydrogen atoms here. Now, if you're identifying something, you want it to be distinct
Mm,
and easy to read
yeah.
so that you know, oh, this definitely belongs to this definitely belongs to that. So you want a technique that will give you different signals.
Yeah.
Yeah. For NMR spectroscopy, in organic compounds, we see a lot of CH3s. we see a lot of CH2s, and it only changes if you have like an oxygen or something that really pulls it one way or pulls it the other.
Yeah.
Petrol is a mixture of hydrocarbons, which means no oxygens, that
Okay.
only differ by their number of carbons
Yeah.
that vary in size. Now, it's possible that some of them are really branched, some of them are unbranched, so you could get unique signals, but in most hydrocarbons, you see a bunch of CH3s and you see a bunch of CH2s.
Yeah.
So the signals in NMR spectroscopy are going to look very similar to each other.
Yeah.
So it's going to be very difficult to identify what the hydrocarbon actually is.
Okay. Yeah.
Okay, so not A. Now, you're not identifying what the hydrocarbon is, though. Your traces of a substance could be petrol. So you're not identifying what the hydrocarbon in the petrol is. You're identifying that it's a hydrocarbon anyway.
Okay. Yeah.
Yeah, which is all of the different signals. And then the issue with that is you're not gonna tell that it's a bunch of mixtures of different things. In an NMR spectrum, you're just gonna see a bunch of lines up, and for all we know, it could be the same hydrocarbon the entire time, not that it's a mixture of a bunch of different hydrocarbons. Petrol is a mixture.
Okay. Yeah.
Yeah.
Mm.
B, UV visible spectroscopy. What information do we get out of that?
Um, was that like, did that have absorbance
Mm-hmm.
as well?
Mm.
Um, because I know that for the graphs for like that, you usually look at where the specific thing that you're trying to find is peaking, and then like the others are like not like absorbed.
Yes. So if the visible part you need, so if the visible part of UV vis aligns with colorimetry uses only visible light. So the visible part you would need a colored solution for, just like colorimetry, but there is a UV component here, so you don't need it to be colored. So from that perspective, it kind of seems like you can use it to identify petrol
Yeah.
because it's not a distinct color. Uh, the UV vis spectrum is wavelength on the x-axis and then absorbance on the y-axis. So then if you get the graph, you'll know what the lambda max is, the
Yeah.
wavelength at maximum absorbance, and then you can go to the data sheet to figure out what has the maximum wavelength. And then it's not functional groups like normal, you call it chromophores.
Yeah.
Pretty much the same thing. And then similar to functional groups though, functional groups are different. Different chromophores have different lambda maxes.
Okay. Yeah.
So then like single bonds, double bonds, da da da. But then they want you to identify petrol.
Yeah.
Petrol is just a mixture of hydrocarbons. You're just going to get a bunch of signals for carbon-carbon single bonds and carbon-carbon, potentially carbon-carbon double bonds the whole time.
Yeah.
And then this graph doesn't tell you how many carbon-carbon single bonds or how many carbon-carbon double bonds it came from.
Yeah.
It just tells you if that carbon-carbon single bond is there. It doesn't matter if it's 1, 2, or 3. It'll have the same lambda max value.
Yeah.
So for all we know, it might not be a mixture of hydrocarbons like we need it to. It might just be one carbon chain with 6 carbons. It might just be one carbon chain with 7. It might just be one carbon chain with 8. Might not be a mixture of 6, 7, 8, 9, and 10.
Okay. Yeah.
So We want something that allows us to see that the substance is that mixture.
Yeah.
UV-Vis will allow us to identify what chromophore is there, which is good. Like you can get information from both. And it might help us figure out what the hydrocarbon is, but we want something that confirms that it's a mixture of hydrocarbons
Okay.
that was being used. C, atomic absorption spectroscopy. What information does that give us?
Like the concentration.
Yes. Titrations give us concentration.
Like of the known like the known thing that you have.
Yes. And is this an organic chemical analysis technique or an inorganic chemical analysis technique?
Inorganic?
Inorganic, which means it works for that lead like we were talking about before. It works. The hollow cathode lamp in your notes it's made out of the element that's being tested,
Yeah.
which usually tends to be a metal element. So atomic absorption spectroscopy won't work to identify carbon and hydrogen atoms, a mixture of carbon and hydrogen atoms at all.
Okay, yeah.
So your answer by the process of elimination is D, distillation followed by mass spectroscopy. Let's figure out why. What does distillation do?
That's separating by um
Boiling point.
yeah.
And would that work for this question? It's a mixture of hydrocarbons, 6 to 10 carbon chain length.
Yeah.
Yes, because we learned from our theory that the longer the carbon chain, the more weak dispersion forces, the higher the boiling point. So the distillation would work. And what does mass spectroscopy do?
It gives you the molar mass of the
Yeah. And is that useful in this case? Would we get different readings for the different components that we've separated? Or would they all have the same molar mass?
they wouldn't have the same molar mass?
They wouldn't have the same molar mass because it's hydrocarbon molecules with varying lengths, with varying numbers of carbon. So at the very least, they would differ by about 12 molar mass because a carbon is 12.
Okay, yeah.
And then they'll differ by more than 12, like maybe 15, 16, 17 to account for the hydrogens that go off as well when you have less or more carbons.
Yeah.
Okay, so we wanted a technique that identified hydrocarbons and identified the fact that there's a bunch of them. So technically speaking, NMR could have worked and UV-Vis could have also worked. The issue was we just couldn't tell if it was coming from one sample or coming from a bunch of different components. Technically, mass spec wouldn't work either. Technically, out of these three, mass spec would have been the worst because it would have just broken up the same way. So the only difference is not really the mass spec part, it's the distillation part out the front that separates it into the different components first.
Okay, yeah.
So if it was distillation and NMR, to be honest, distillation and NMR is probably better than distillation and mass spec
Okay, yeah.
because mass spec just tells you the molar mass, whereas NMR tells you what the carbon chain actually looks like.
Yeah.
So it's not really the mass spec or the spec part, it's pretty much the distillation part because this is a mixture and we needed ways to confirm that it was a mixture that could be separated into the different components.
Okay, yeah.
Question 11, the 1H NMR spectrum of an organic compound has 3 unique sets of peaks. A single peak, which is a singlet, 7 peaks a septet, and 2 peaks a doublet. Okay, 3 unique sets of peaks, which the different numbers of peaks tells you what. There's the 3 pointers are chemical shift, integration, and splitting.
Yeah.
The 3 peaks tells you which one of the 3.
The splitting.
No. No, this isn't little peaks. This is 3 sets of peaks.
Oh, the integration, like the
Integration is how tall it is. how tall each peak is. This tells you that there's 3 sets of peaks. Things only have a peak in the same spot if they produce the same signal, which means they look the same. So sets of peaks tells you the chemical environment.
Yeah.
And then the splitting tells you what?
Like how many neighbors?
Yes, good. So if it's a singlet, how many neighbors?
0,
0 neighbors. If it's a septet, how many neighbors?
6,
6 neighbors. And if it's 2 peaks,
1.
how many? 1 neighbor. Good. Okay. How do we draw a 3-methylbutanoic acid?
4 carbons,
2, 3, 4.
and then that's double bonded to OOH.
Mhm.
And then from right to left is is methyl.
Yep. And then fill the rest in with hydrogen. Okay. I'm going to condense this one into a CH3 as well.
Okay, yeah.
All right. So we're doing hydrogen environments. These 3 hydrogens are on the same carbon.
Yeah.
These 3 hydrogens are also on the same carbon.
Yeah.
But both methyls end up bonded to the same carbon.
Yeah.
So although their first carbon is different, they end up the same way. This looks the same as this.
Yeah.
So these 6 hydrogens have the same environment.
Okay, yeah.
These 2 hydrogens are bonded to the same carbon,
Okay, yeah.
but these 2 hydrogens bonded to the same carbon. This hydrogen is bonded to an oxygen.
Yeah.
And this is also a single hydrogen, but it's bonded to a carbon. This single hydrogen is bonded to an oxygen. Different bonding won't have the same environment.
Yeah.
So how many environments in total?
4.
4. So we want 3 sets of peaks, 3 chemical environments, but we've ended up with 4. So A is not your answer.
Okay, yeah.
How do we draw B? 2-methyl propanoic acid.
3 carbons,
3 carbons,
and then double bonded to OOH.
double bonded to OOH.
And then in the middle is methyl.
Mm-hmm. And then I'll fill in the hydrogens with a condensed formula as well. Okay. Same thing as before. These 6 hydrogens onto their own carbons, but then they end up bonded to the same carbon.
Yeah.
And then this one. And then this one.
Yeah.
Okay, so 3 environments as required. We want no neighbors, 7 neighbors, and we want no neighbors, 6 neighbors, and 1 neighbor. So these 6 hydrogens
Yeah.
in blue, how many neighbors do they have?
Um, was it, wait, 2?
2. You only want any hydrogens on the carbon that it's directly bonded to. You don't want to look any carbons over.
1.
1. So these 6 hydrogens, it only is attached to 1 carbon, which is this one here. So you only look on that carbon to see if there are any hydrogens on it.
Okay, yeah.
It's bonded to this 1 hydrogen, so that 1 hydrogen is a neighbor. This hydrogen here is 2 carbons over, and not even 2 carbons, it's 2 carbons and 1 oxygen over.
Yeah.
So we don't count that oxygen in the OH. And then also because the hydrogen's in an oxygen, it just won't have any neighbors to begin with. It's not even in a carbon house.
Yeah.
So these 6 hydrogens have 1 neighbor. What about this single hydrogen, how many neighbors does this one have?
1.
One? One hydrogen as a neighbor?
0.
0. So this hydrogen is bonded to this carbon. We're not looking at that carbon. We're looking at any carbon houses over. It's already in this house. So you look around and this house that it's in has this house as a neighbor, has this house as a neighbor, and has this house as a neighbor.
Oh, okay, yeah.
And then you're like, okay, this house doesn't have any carbons attached to it, so there's no neighbors in that house. This house that I'm neighbors with has 3 hydrogens living in it. This house that I'm also neighbors with has 3 hydrogens living in it. So in total, it's got 6 neighbors.
Okay, yeah.
And then last one is your hydrogen in the OH. How many neighbors?
0.
0, good, because it's not even in a carbon house. It doesn't have any neighbors at all. Oh. So this matches. We wanted 0, 6, and 1. So your answer is B.
Yeah.
Okay, let's have a go at the other two for practice. How do we draw 2-chloro-2-methyl propane?
3 carbons.
1, 2, 3.
And then in the middle is methyl and Cl.
And then I'll fill this in condensed as well. Okay. These 3 hydrogens bonded to 1 carbon.
Yeah.
These 3 hydrogens, let's change the color. These 3 hydrogens bonded to another carbon.
Yeah.
These 3 hydrogens bonded to its own carbon.
Yeah.
But together, each separate group looks the same. They're all CH3, CH3, CH3s.
Yeah.
And then if each CH3 was bonded to a different carbon, they wouldn't have the same environment, but they look the same and they end up bonded to the same thing.
Yeah.
So all of them, all 9 hydrogens, have the same chemical environment.
Yeah.
So there's no more hydrogens. I've exhausted all of it. So there's only one signal and it's integrated to 9 hydrogens.
Yeah.
And then I'm like, are there any neighbors? So these 9 hydrogens are in this house.
Okay, yeah.
And then when I'm looking for neighboring protons, I don't want to look in that yellow house that it's already in. I'm looking at any house that's next to it because that's what a neighbor is.
Yeah.
My neighbor is the one right next to me on the road. And then any other houses outside of that is in my neighborhood, but they're not technically my neighbors. They're not directly to the right or to the left of me.
Okay, yeah.
I'm not looking at my own house. I'm looking at any house right next to me on the left or right next to me on the right. If it's 2 houses or 2 carbons over, they're in my neighborhood, they're in the molecule, but it's not my neighbor.
Yeah.
So the yellow house is where I'm in, and then I'm like, am I attached to any other house directly? I'm attached to this one.
Yeah.
That's the house. I don't actually think that that's my neighbor. That's the neighbor's house. The neighbor is the person living in the house.
Yeah.
And then I'm like, any hydrogens bonded to this carbon house? There are none. There's no hydrogens directly bonded to that carbon, so 0 neighbors.
Okay.
So you have one signal integrated to 9. 0 neighbors means it's a singlet and it doesn't have any splitting.
Yeah.
Okay. How do we draw D? 1,2-dichloro-2-methyl propane.
3 carbons.
3 carbons.
And then in the middle is methyl and then 1 Cl.
Yeah.
On the first is another Cl.
Okay. And then I'll condense this as well. And then I'll condense this. They're attached to the same carbon. Okay. These 3 hydrogens bonded to 1 carbon.
Yeah.
These 2 hydrogens bonded to 1 carbon.
Yeah.
And these 3 hydrogens bonded to 1 carbon.
Yeah.
So I have a CH3, a CH3, and a CH2. The CH2 doesn't match just by hearing the name. You could tell there was two, not three. So this one is definitely on its own. It's going to produce one signal. Let's check if the other two CH3s are bonded to the same carbon, and then maybe they end up having the same signal.
Yeah.
These two CH3s here, they look the same, but they're in their separate houses, but they end up bonded to the same thing.
Yeah.
So they look the same and they end up bonded to the same thing. So they do have the same chemical environment.
Yeah.
So I have two signals. One is integrated to, one of them is integrated to two CH3s. And then the other one is integrated to two because it's a CH2.
Okay. Yeah.
Let's start off with the ones integrated to 6. This is the house that it's in.
Yeah.
For me to look for the neighboring protons, I'm looking at my neighboring house. This is the carbon that it's directly bonded to. I ignore this carbon, it's 2 carbons over.
Yeah.
So I'm looking at this blue carbon, I'm looking what's bonded to the left, right, top, bottom of it, and it's three carbons and a chlorine down the bottom.
Yeah.
So that carbon in blue doesn't have any hydrogens on it at all, which means the house next to me has no one living in it,
Oh, okay. Yeah.
which means no neighbors for me in the yellow house.
Yeah.
So I have two signals. The one that's integrated to 6 has no neighbors, which means it's got no splitting and it's going to be a singlet.
Yeah.
Okay. Okay. And then now now I've moved houses. I'm now in the CH2 house.
Yeah.
So I'm probably living in there with a friend because it's two hydrants living in that one house. And then once again, I'm looking directly left, right, top, or bottom of me. Left and bottom, there's nothing. I haven't drawn anything there. Top, there's a chlorine. Right, there's a carbon. That's a neighboring house.
Yeah.
But that happens to be the same carbon as before, which we identified doesn't have any hydrogens on it.
Yeah.
So even though there's multiple hydrogens and multiple signals, they aren't next to each other. The CH2 and the CH3 aren't next to each other, so they're not neighbors.
Yeah.
No neighbors. That's also a singlet.
Yeah.
Any questions?
I remember you told me a rule like for the CH3s and CH2s.
Mm.
What was that again? Because I don't, yeah, because I remember you told me there was something, I think it was with how many it was integrated, and then um, like,
Oh, that was for reading the spectrum, not for interpreting it yourself. So we said if you see, because CH3s tend to be together and CH2s tend to be together. So we were just saying, like, when you read a signal and if they tell you that it's integrated to 6, that's a group of 3. So that's probably 2 CH3s.
oh, okay, yeah,
Yeah. And then like if you see something that can't make that can't make multiples of 3, if you see something like integrated to 5, that might be a CH3 plus a CH2.
okay,
Yeah. But then like if you see something integrated to 4, it's more likely to be a CH2 on either side of it.
yeah,
It could be a CH3 on one side and then like just a single hydrogen on another carbon, but very unlikely.
okay, yeah,
Normally you'll see groups of 3s or a group of 3 mixed with a group of 2.
okay,
That
yeah,
was for reading the spectrum.
okay, yeah,
Anything else?
and
Okay. Let's have a look. We have one gravimetric analysis question, but then there's I put in quite a few precipitation titrations in here because you can't never really get enough of those.
it's so true.
I will miss your sarcasm. Question 12, magnesium is precipitated out of a 150 ml sample of water as magnesium oxide. A 35-gram crucible is containing the precipitate weighs a total of 37.15 grams. Calculate the concentration of magnesium in grams per 100 mils of water. Okay. The reason I know this is a gravimetric analysis question is because I put it in, but let's say we're in the exam.
Yeah.
There's quite a few masses going on, and then also you normally weigh things as a mass by precipitating it out of solution. So if you see precipitate and you see mass, it'll normally be a gravimetric analysis question. It won't be precipitation titration because with titrations, we don't care about mass. The precipitate gets formed, yes, but titrations is more concerned with volume.
Okay, yeah.
So if you see precipitate and volume, normally precipitation titration. If you see precipitate and mass, probably gravimetric analysis.
Okay, yeah.
Anytime you see calculation questions, once again, and it's not like a Q is equal to MCAT where the equation is really obvious. It's normally every chemistry question tends to be a stoichiometry question. So identify what the chemical is they've given you information for, what chemical they're asking you for, what equation do you write to relate the two.
Yeah.
So this case, magnesium is precipitated out as magnesium chloride. So magnesium chloride is the precipitate, and that precipitate is 37.15 grams. So they've given you information for the precipitate.
Okay, yeah.
And they've asked you for just the magnesium itself. So they've given you information for one, asked you for another. I either need an equation or I could just use the formula.
Okay, yeah.
Now, the reason the formula, sometimes we use chemical equations instead of formulas, and sometimes that's because elements show up in a bunch of different places. So like let's say you know how in year 11 you did balancing equations and then you balance entire molecules. However, you also can't lose the element that you have.
Yeah.
Like you can rearrange the bonding, but if you had 6 oxygens at the start, you will have to have 6 oxygens at the end.
Yeah.
So that's the whole point of balancing the equation anyway. You're making sure the elements are balanced. So if you can't figure out an equation, this only works if they're asking you for the element.
Okay.
Like they've given you the molecule and they're asking you for the element.
All right. Yeah.
Because we know that whatever elements there were at the start, it has to show up in the molecule at the end of the reaction.
Yeah.
Yeah. But like the reason I'm trying to explain why sometimes we use the equation and sometimes we can just rely on one single formula. The reason why sometimes we use the equation is because they're not asking you for an element. In previous questions that we've done, like in that module 7 question with the ethanol and the combustion, they gave you information for ethanol, which is one molecule, and they asked you for CO2,
Yeah.
which is not an element.
Okay.
You can't see the formula CO2 in the ethanol formula.
Yeah.
So for that, you have to relate it with an equation.
Okay.
However, in this case, they've given you magnesium oxide, and it's not like they asked you for magnesium dioxide. They didn't ask you for magnesium carbonate. They asked you for magnesium.
Yeah.
Yeah, which means I don't really need to write the chemical equation for this. All of the magnesium shows up in the magnesium carbonate. So it's kind of like when you're doing stoichiometry, you know, when you're doing like module 6 acid-base stuff and you're like, oh, mole, and then you're like, the moles of H2SO4 is 2, And then H2SO4 is diprotic, it releases 2 hydrogens. So the moles of H plus must be 4.
Yeah.
It's similar to that. You didn't need an equation for this because you were relating one molecule with one element.
Yeah.
If you were relating different molecules together, you can't see one molecule in another molecule because it's rearranged. So you will have to write the equation.
Okay.
In this case, I can just do the formula.
Yeah.
Now, so they've given us a 35-gram crucible containing the precipitate weighs a total of 37.15 grams. So is that 37.15 the mass of the precipitate?
Um, no.
It's the mass of the precipitate plus.
Um, like the product
Well, the
is,
precipitate is the product.
or
The 37.15 grams is a total of the precipitate and because they said weighs a total of
the crucible.
crucible. Good. So what do I do to get just the mass of the precipitate out?
You minus 35 from 37.15.
Yes, so the 37.15 is the entire precipitate, which means that, sorry, is the precipitate plus the crucible. So if I want just the precipitate, I do precipitate plus crucible minus crucible gives me precipitate, which is 2.15 grams.
Yeah.
And then when I get given one chemical but get asked for another, I need to do that in terms of moles. So moles of MgO is going to be mass on molar mass is 2.15 grams divided by, what's the molar mass for magnesium?
24.31.
24.31, and then oxygen is 16. So what's the molar mass of magnesium oxide?
That's 0.05.
0.05 dot 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 mole, and all of the magnesium is precipitated out as magnesium chloride. So what's the ratio of magnesium to magnesium oxide, sorry?
1 to 1.
1 to 1. So if it's 0.05 moles of magnesium oxide, the moles of magnesium must also be 0.05.
Yeah.
And then they want the concentration in grams per 100 mils. So mass in grams is moles times molar mass, which is 0.05 dot 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 mole times 24.31 grams per mole.
That's 1.29.
1.29 grams. So I've got the mass now. They want it per 100 grams. That 1.29 gram, they want it per 100 mils. That's currently in the moment 150 mils.
Yeah.
So if I put it as a fraction, 1.29 grams divided by 150. How do I turn 150 into 100?
150 on 100.
Yeah, I times by where I want to end up and I divide by what I want to get rid of. So like
Oh,
technically I'd be timesing this whole thing by 100 on 150.
yeah.
But because it's in the denominator, it flips. So the whole thing would be times by 150 on 100.
Yeah.
Okay. So that 150 cancels out and I'll just end up with 100 mils down the bottom.
Yeah.
So what, actually no, hold on. 1.29 grams per 150 mils. I can't, no, we can't do it like this because if you put this in the calculator, what you end up with is if you put the entire thing in the calculator, you'll end up with per mil down the bottom anyway. Like if you divide by the 100, it'll just end up being per mil.
Okay, yeah.
So what we want to do instead, so it's 1.29 grams for every 150 mils.
Yeah.
Let's do it on a per unit basis because it's easier to do unit conversion. Sometimes it's easier to do it this way. If you're converting between different units, it tends to be okay. But if you're converting by the same unit, just different numbers, it's a little bit confusing.
Okay, yeah.
So let's go to what it is per mil first, and then I'll scale back up to 100 after.
Okay, yeah.
So for me to go per mil, I divide by 150. So how many grams per mil?
That is 8.6 times 10 to the minus 3.
Times 10 to the minus 3 grams. And then I'll scale back up to 100 mils. So I'll
Mm.
times 100 to get 100 mils. And then I'll do the same thing with my mass.
And that's 0.86.
0.86 grams. So then what I'm going to do now, because I have it per 100 mil, when I put it back in the fraction, I will not sub it in the calculator. My answer is 0.86 grams per 100 mil.
Okay, yeah.
Yeah, so when they say per 100 mil, they actually want it kept in the denominator. Because if you try putting this in the calculator, if you do 0.86 divided by 100, you'll end up with 0.0086. But then because you've divided the 100 now, that ends up being grams per mil, which is what you had up here.
Oh, okay, yeah.
Yeah, so when you see per 100 mil, you actually want to keep the 100 down the bottom so you don't sub that into the calculator.
Okay, yeah.
Yeah. So I rubbed off the wrong one. That's going to be your answer. This one here.
Yeah.
Any questions?
No.
Okay. Question 35. 35 mils. Question 13. 35.7 mils of 0.1 molar silver nitrate was required to reach the end point of a titration with 75 mils of a chloride solution. Calculate the concentration of the chloride solution. This is a titration question, but the chemicals they've given you aren't acid bases. They are ionic compounds. So this is how we know it's a module 8 precipitation titration, not a module 6 acid-base titration.
Yeah.
But all of the steps are the same. You're just writing a different equation. So only two chemicals here. You can only write one equation. That has to be a direct titration. There's no words excess, so it's not a back titration.
Yeah.
So I'm just writing one equation. What's the formula for silver nitrate?
AgNO3.
AgNO3. And then they haven't told me what the chloride is in. So I can't do like NaCl. I can't do AgCl. It's just going to be Cl minus.
Okay, yeah.
And then the ions still swap. So AgClS and then NO3 minus comes out instead.
Yeah.
And then like with any acid-base titration from module 6, if you get asked for the acid concentration, you start with a base. If you get asked for the base concentration, you start with the acid. In this case, they're asking you for the chloride, so you just start with the silver nitrate.
Yeah.
So moles of AgNO3, C times V, 0.1 molar times 0.0357 liters gives you 0.00357 moles. And then what's the moles of the Cl minus going to be?
The same amount.
Yeah, moles of Cl minus is going to be moles of AgNO3, 0.00357 moles. And then they're asking you for concentration. So that's N on V, 0.00357 moles divided by, it's 75 mils, but we sub in 0.075 liters. What's our concentration of chloride?
0.0476.
476, and we have a 0.10 molar here, so that's 2 sig figs. So I have to go down, which is going to be 0.048 molar to 2 sig figs.